Good evening to all, and welcome to the another session of the NPTEL course Heat Transfer. So today we will be discussing about the week 7 topics. So the let's have a brief overview or recap about the week 7 topics. So week 7 topics was internal flow, means internal flow heat transfer, where the flow was taking through a circular tube or duct. So in the previous weeks, we will be discussing about the flow over a flat plate. Now, here the flow is taking over a confined surface. For example, flow through a pipe or a duct, etc. So in internal flow heat transfer, first we first discussed about the thermally, sorry, hydrodynamically fully developed conditions where the velocity profile does not changes with respect to the x-axis or the in the flow direction. Then we discussed about the thermally fully developed conditions, where in thermally fully developed conditions, the velocity means the temperature in we cannot have a direct uh, thermally fully developed condition means for hydrodynamically fully developed condition we use the term dou u by dou x is equal to 0, but the same condition dou t by dou x, okay, we cannot define that dou t by dou x is equal to 0 as a thermally fully developed condition, because as the heat is getting transferred to the fluid or getting rejected from taken away from the fluid, the temperature will be increasing over the length of the pipe. So for defining the thermally fully developed conditions, we defined a non-dimensionalized temperature, and we differentiated or variation of that non-dimensionalized temperature with respect to x. If it is equal to 0, that we will be considering it as a fully thermally fully developed. Then we move on to the flow two um, conditions like constant heat flux conditions and constant temperature conditions, and the governing equations for both the conditions were also discussed, and also the Nusselt number for these conditions for a fully developed flow was also derived. Then 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 the laminar flow conditions. So this basically we mostly we discussed about laminar flow conditions at the last lecture. Turbulent conditions and Ditterboyd equations for Nusselt number for turbulent flow over a inside a pipe, etc. was also discussed. So this was a brief overview about the week 7 topics. So let's do some practice questions based on the week 7 topics. So let's get started with the first question. So in this question, a water enters a pipe at a rate of 0.01 kilogram per second and the temperature 20 degrees Celsius. The pipe has a diameter of 50 mm and the length 3 mm is subjected to a wall heat flux of 2500 x watts per meter square. Means it's like it's not a constant heat flux, it's a function of x. This is 2500 x watts per meter square. So we need to find out what is the bulk mean temperature of the water leaving the pipe. So let's draw the schematic. We have a pipe. Okay. So water is entering at 0.01 kilogram per second, and temperature Ti is 20 degrees Celsius, and the diameter of the pipe is given as 50 mm, and the length of the pipe is given as 3 meter. So water will be, and we have a heat flux, and the pipe is subjected to a constant, not constant, it's a function of x, that is Ux is equal to 2500 x watts per meter square. Okay. So we need to find out what is the exit temperature of the pipe under these conditions. So we know the Q total heat that is transferred to the fluid is equal to m dot Cp To minus Ti. So this heat is transferred because of the applied heat flux. So we need to find out what is Q total. Q total is equal to integral Qx A dx dx, right? 0 to L. Because if I am taking a small elemental strip of length dx, so what is Qx for this elemental strip? Or for what is the heat transfer? Heat that is transferred, that is Qx, is equal to Qx into, it's a heat flux, that is area, that is what is the perimeter, that is Ax, that is perimeter is constant, that right. So there is no this is not Ax, this is AP. We can write it as AP, that is I mean it's not a perimeter. So this is into TAX, right? This is the actual expression. This is for this elemental area, this elemental surface area. What is this elemental surface area? This perimeter, that is P, that is constant into dx. This is the area through which the heat is getting transferred. So I am rewriting this as integral Qx P dx. Right. So through over the length 0 to L. So we just need to calculate 0 to L 2500 x into pi into d into dx. Right. So if we calculate it, 2500 pi d x square by 2 L to 0, which is 2500 pi d L square by 2. So this is the total heat that is transferred along the length of the pipe. So if we calculate this, 2500 into pi into d is 0.05, that is 50 mm, into length is 3 square, that is 3 meter square to 2. So if I calculate this, I will get it will come up to be around 1766.25 watts. So just substitute this into this expression, that is 1766.25 is equal to m dot Cp To minus Ti. M dot is given 0.01 and I am taking Cp as 4127 into To minus Ti. So what is Ti? You can easily calculate. It's divided by 0.01 star 4127 plus what is the initial temperature 20. 62.8 degrees Celsius. Okay. So this is the exit temperature of the pipe. Sorry, exit temperature of the water. 62.8 degree Celsius. So the answer to this question is B. So I hope this was clear. This was a simple question. It's just an energy balance. But the only thing we need to consider is here the heat flux is not a constant value. If it was just a constant value, we just need to multiply the heat flux with the surface area and equate it. But as here in this case, here heat flux is a function of x, we just need to apply integration. Okay. So let's move on to the next question. The next question is also based on the same first question. So if the heat flux is constant at 500 watts per meter square and the heat convection heat transfer coefficient at the outlet is 1000 watts per meter square Kelvin, we need to find out what is the inner surface temperature of the pipe. So we have a pipe outlet. So here we know what is the heat flux. So and the inner convection heat transfer coefficient is also given. So just apply our, that is our energy balance equation. Q is equal to H T surface minus T surface minus T O. Right. So this is our expression. So we need to find out what is Ts. We already found out what is TO, right? That is from the surface, it is transferring to TO. So 5000 is equal to 1000 into Ts minus TO is 62.8. So Ts is equal to 62.8 plus 5, which is equal to around 67.8 degrees Celsius. So this is the answer. Okay. So let's move on to the next question. For a flow through a pipe of radius r, the uh, velocity and temperature distribution is given. Okay. So we need to find out what is the mean temperature. So I think this is a gate question. So we need to find out what is Tm, that is mean temperature. So we know the expression for Tm, but is I'm not deriving that expression, it is derived in the lectures. Q divided by um square r square, integral 0 to r u rx d rx into r dr. So this is the general expression for the mean temperature, right? It's not square, it's just u. This is the expression for sorry, Tm. So you just need to substitute these values, that's all. So u of rx is given, T of rx is given, but we need to find out what is um. Also we have another expression which is 2 by r square integral 0 to r u r of x r dr. Right. First we need to calculate what is then only we can find out what is Tm. That is 2 by r square integral 0 to r c1 r dr. Right. So it is 2 c1 r square by r square into 2. If you integrate, c1 is a constant. So c1 is a constant. Okay. So if you cancel this, we will get what is the value of as c1. Okay. So then we need to find out what is the Tm, temperature, the mean temperature. So just substitute these values, that is Tm is equal to 2 by r square integral 0 to r u rx t rx r dr. So 2 by cm r square integral 0 to r c1 into c2 times 1 minus r by r the whole cube r dr. Okay. So let's take the common constants out of integration. C2 by c1 r square is 0 to r 1 minus r cube divided by r cube r raised to 4 r raised to 4 dr. So this gets cancelled. 2c2 by r square is 0 to r square by 2 minus R raised to 5 by 5 R cube R 0. That is 2C2 divided by R square by 2 minus R raised to 5 by 5 R cube. So this becomes 2C2 divided by R square by 2 minus R square by 5, 2C2 divided by R square into 3 R square divided by 10, R square cancels. So it becomes 6 by 10 C2, or we can write 0.6 C2. So this is the answer. This is our answer for. So this is the expression for our mean temperature. Mean temperature. So if you look, we can see that the Tm is constant. Tm is constant. Its Tm is not a function of R or X. Right? It's just a the Tm is constant everywhere. That is, if the C2 is a constant, the 0.6 is a constant. So Tm, it is mean temperature at any location, will be constant. Okay. Let's move on to the next question. So a water flows through a 2.5 centimeter internal diameter thin copper tube of a heat exchanger at 15 degrees Celsius at the rate of 0.3 kilogram per second and is heated by steam condensing outside at 120 degrees Celsius. If the average heat transfer coefficient is 800 watts per meter square Kelvin, determine the length of the tube required to heat the water to 115 degrees Celsius. So I will just draw the schematic. Uh, Water is flowing through a copper tube of size 2.5 centimeter, and the water is entering at the rate of 0.3 kg per second and at 15 degrees Celsius. Is entering at 50 degrees Celsius. And we need to, the water should exit the tube at 115 degrees Celsius. And the heat transfer, average heat transfer coefficient H is also given. It's 800 watts per meter square. And the steam is condensing outside. So the temperature, surface temperature is constant at 120 degrees Celsius. So as I mentioned, this is the second case. So for the first case is for the first question we have discussed, which is the when it is subjected to a heat flux condition. Now it is subjected to a constant temperature condition. So the how we have to proceed means how we are the governing equations and all are discussed in the lecture. I'm not going into that. I'm just taking the final results of that to solve this question. Okay. So in the case of when it is a constant surface condition, constant surface heat flux constant surface temperature conditions, we need to use the log mean temperature, that is Q. This total heat transfer is equal to HA delta Tm. It is a log mean temperature difference we need to use. Because how it comes, why we need to use log Tm difference, how it comes, it's all are discussed in the lectures. You can refer back to the lecture. So what is log mean temperature difference? Delta Tm is equal to delta Te minus delta Ti divided by L delta TE divided by delta TI. So what is delta TE? That is TS minus T exit. For our condition, our case, it is 120 minus 150, which is 5. Delta Ti is equal to Ts minus Ti, which is 120 minus how much? 50. Is 105. So let's substitute this into these values. 5 minus 105 ln 5 divided by 105. So the answer, so the log mean temperature difference is 32.84 degrees Celsius. Now just we need to substitute this value, substitute into this expression, that is. This should be equal to the enthalpy gain. It is there, you see, TO minus TI. So H is given. H is given as how much? 800. Then what is the area of heat transfer? That is perimeter pi into d into the length. This is we need to find out. Into 32.84 should be equal to 0.3 times specific heat 115 minus 50. So the length L is equal to 0.3 into 4187 into 100 divided by 800 into pi into what is D 2.5. We are converting into meters. Pi D into 32.84. So the answer will come out to be is 60.9, or approximately we can write 61 meters of length is needed for this tube to have a temperature change of this much under this condition, which means the length of the tube should be around 61 meters for to heat the water from 15 degrees Celsius to 115 degrees Celsius, having a mass flow rate of 0.3 kilogram per second, and the steam is condensing when the surface temperature of the tube is maintained at 120 degrees Celsius. So this is the answer. Let's move on to the next question. The water is to be heated from 15 degrees Celsius to 65 degrees Celsius as it flows through a 3 centimeter internal diameter 5 meter long tube. The tube is equipped with an electric heater that provides uniform heating throughout the surface of the tube. The outer surface is well insulated so that in steady state all the heat generated in the heater is transferred to the water. If the system is to provide hot water at a rate of 10 liter per minute, determine the power rating of the heater. This is also a simple question that all the similar kind of questions I already discussed in the previous session. So I just draw the schematic. we have a two pipe. It should be heated from 15 degrees Celsius to 65 degrees Celsius. And the internal diameter is 3 centimeter and it's a 5-meter long tube. So it should provide water at a rate of 10 liter per minute. Okay. So we need to find out what should be the power rating, the power rating of the heater that is wound to the surface of this tube, so that we will get this conditions. So that we will get the water delivered at 10 liter per minute at 65 degrees Celsius at the exit. That is the question. So first we need to find out the mass flow rate of water, that is rho V, that is it is given, that is 992.1 into 10. We need to convert it into meter, 10 raised to minus 3 meter cube. We need to convert it into seconds, 60. Okay. So we get it as 0.165 kilogram per second is the required mass flow rate of the for this case. Next, Q is equal to m dot Cp To minus Ti. What we need to find out, what is the power rating of the heater, that is Q. How much is the Q that is required? That is 0.165 Cp. How much? It is given 4179 into 65 minus 50. So how much would be? It is around 34 or 76.75 watts. If I converted to kilowatts, it is 34.76476 kilowatt. So this should be the power rating of the heater if we want to get water at 65 degrees Celsius with this flow rate. Okay. I hope this questions was also clear. So just in continuation of this question, based on question 5, we need to estimate what is the inner surface temperature of the pipe at the exit. I think the same question I have already done. So pipe at the exit. So in the difference between that first, I think it was second question, right? Quick. The difference between this, the way we need to do is same, but the difference is their heat transfer coefficient was given, but in this question it is not given. That is the difference between the second question and this question. So our major task is to find H, that is the heat transfer coefficient. So let's find out what is the. So we already studied that if it is a laminar flow, the Nusselt number for a constant heat flux condition is 4.36, and for surface temperature condition is Nusselt number is 3.6. So just we need to check whether this is laminar or turbulent. So for that we need to find out the Reynolds number, that is Re. So that is how much? That is rho u mean T by V. So first we need to find out what is UM, that is the mean. That is the volume flow rate divided by the area of cross section. It is given what is the volume flow rate 10 into 10 raised to minus 3 divided by 60 into what is area's cross section pi by 4 into 3 into 10 raised to minus 2 the whole square. Okay. So if we calculate this, we will get 0.235 meter per second. This is the mean velocity of flow. So just we need to calculate what is the Reynolds number. So these all properties are calculated at the mean temperature. So that is 15 plus 65. How much? 80. Right? 80 by 2. That is 40 degrees. So these properties are calculated at the mean temperature 40. So the rho it is given how much? 992.235 into 0.03 by mu is given how much? Okay, so already this mu is given, so the kinematic viscosity is given, so there is no need of dynamic viscosity. We can write the answer as um a by mu, because mu by rho is the dynamic viscosity by rho is the kinematic viscosity mu. That is already given, directly given in the question. So 0.25 into 0.03 divided by 0.658 into 10 raised to minus 6. So the answer to this question will come out to this. So which is the turbulent flow. So, so we cannot use the laminar flow correlations here because Reynolds number is greater than the critical Reynolds number, that is 2300 for a pipe, circular pipe. So here we need to go for the laminar, so turbulent flow correlations. So the lecture it was discussed means is given that for turbulent flow we will be using Litter-Poitras equation. That is the Nusselt number is equal to 0.023 Reynolds number raised to 0.8 Prandtl number raised to n, where n is equal to 0.4 for heating and n is equal to 0.3 for cooling. So here this is a heating condition. Means the water is gaining energy, or the temperature of the water is increasing, so it is gaining heat. So for this case it is 0.023 Reynolds number raised to 0.8 Prandtl number raised to 0.4. So here, so this for applying these conditions we need it should be less than, Prandtl number should be less than 150 in this range. Reynolds number should be greater than 10,000. So all these conditions got satisfied. So it's a like so the length of the tube, yeah. So the length of the tube is greater, L by D should be greater than 10. So L by D, so D is 0.03 into 10. So L is 5 meter, the diameter is 3 meters. So its L by D is greater than 3. So all these condition satisfies. Okay. So we can use this Litter-Poitras equation for this question. So the substitute is 0.023 Reynolds number raised to 0.8, Prandtl number is 4.36. 1.32 raised to 0.4. So the Nusselt number will comes out to be 69.5. So now we know this Nusselt number is equal to HD by K. So H is equal to 69.5 into K is also given 0.61 divided by what is D, 0.03. So the answer comes out to be 11462 watts per meter square. So you can do the math. So now we got the H. So that was necessary to calculate uh, our what was our question to find out the inner surface temperature. So we know Q by A surface is equal to H T surface minus T outer of at the exit. Okay. So here the heat flux is constant because it's not varying with air. It's like so 34.4 what was 476 to 10 raised to 3 divided by pi d L is equal to H T surface minus T. So this will come out to be around this will be 73.2 into 10 raised to 3 watts per meter square. This heat flux divided by H1462 plus T outer is equal to T surface. So divided by 1462 plus what is the outer surface is given 65. So the surface temperature at the exit is 115 degree Celsius. So, so the means main part of this question is to find out H. If we get H, we just need to substitute in the equation. So okay, I hope that question was clear. So let's move on to the next question. Hot air flows with a mass flow rate of 0.5 kilogram per second through an uninsulated sheet metal duct of diameter 0.15 meter. Hot airs enter at 103 degrees Celsius and after a distance of 5 meter cools to 85 degrees Celsius. The heat transfer coefficient between the outer surface and ambient is at 0 degrees Celsius is 6 watts per meter square. Calculate the duct surface temperature at x is equal to L. The exit. So we have a surface, we have a duct. Okay. So air is entering at 0.05 kilogram per second at 103 degrees Celsius. And after the length is 5 meters. The diameter is given as 0.15 meter and it leaves the duct at 85 degrees Celsius, which means the cooling is happening. Means the air is rejecting heat to environment. The environment T infinity is at 0 degrees Celsius and HO is given as 6 watts per. Okay. You need to find out surface temperature at X is equal to L, which means 5 at the exit of the pipe or the duct. So this is a given things in our question. So our basic expression that is Q is equal to m dot Cp Ts or To minus Ta. So let's see how much will be the heat loss from the air. That is, m dot is given 0.05, Cp is given 85. Here as it is cooling when is so it's minus because its air is rejecting heat. Okay. So this much amount of heat should be taken out from the air. So let's take the network analogy. I take it the mean temperature at L, then the heat transfer coefficient at L, surface temperature at L at T infinity. This is 1 by HO. Outer surface. This HO is given. HO is given. It is fixed. That is the heat transfer coefficient at the outer surface of the ambient is given. That is 6 watts per meter square. So this Tm is also given. That is T mean temperature is 85. So we want to find out the surface temperature TSL. For that we need to find out what is HXL. So for that we need to find out what is uh, we need to find out the heat transfer coefficient at L. So let's check which correlation we can use or which expression we can use. First we need to find out the Reynolds number. Okay. So mass flow rate is given. This is rho A V. So what are the things it is given? So we have the direct expression, right? M dot is equal to rho V pi by 4 t square. Okay. So rho V d is equal to 4 m dot divided by pi. Okay. So it's 4 m dot by pi mu, the Reynolds number. 4 into what is m dot 0.05 pi into mu is given 211 volts. Here the dynamic viscosity is given. In the earlier question we use the kinematic viscosity. So please be careful which viscosity is given in the question. So the Reynolds number will come out to be around 20,050. So which is turbulent. Okay. So we can use the Dittar-Boyton equation because uh, it is satisfying all the criteria for this. So Nu is equal to 0.023, Reynolds number raised to 0.8, Prandtl number raised to 0.3 here because 0.4 for heating and 0.3 for cooling. 0.023 into Reynolds number is 50.8 into 0.698 raised to 0.2. So the Nusselt number will come out to be 56.4. So if you take the local you take the heat transfer coefficient Nu d sorry k by Case. So the heat transfer coefficient will come out to be around 11.5 watts per 11.5 watts per meter square Kelvin. So what is the resistance? So the heat flux we need to calculate heat flux. So the heat flux at L at exit, that is T Tml minus T infinity divided by 1 by Hx plus 1 by Ho is 85, sorry, 85, 85 minus 0 Ho. So the answer will come out to be 335 watts per meter square. Is the heat flux at the exit. So now just substitute this into just Tm, sorry, Tml minus Ts divided by 1 by Hx. That is, the Ts will be Q double dot by Hx plus Tml. So the answer will come out to be sorry, so the surface temperature will be come out to be around 55.87 degrees Celsius. So this will be the surface temperature. So the closest answer is 56 degrees Celsius. Okay. So here we need to calculate the local heat flux, because here in this question it is not given, means how the heat is means it is a cooling process. We are just means and means admitting the air at 103 degrees Celsius, and because of heat loss to the environment, basically it is getting cooled to 85 degrees Celsius. So we need to calculate, so the heat flux may be different, and the surface temperature may not be also constant, it will be also vary. So we need to find out the local heat flux, then the surface temperature at the exit. Okay. So here comes to the end of our session, and thanks for watching this question, this practice question session. And so we will meet you in the next Monday with the practice questions for week 8 topics. So See you soon. Have a nice week ahead. Thank you.